Today we will do Nernst equation. Nernst equation. This equation is to find out electrode potential of a half cell or electrode potential of an electrode assembly when the conditions are not standard. Condition standard means you have seen that concentration should be 1 molar and temperature should be 298 Kelvin, that is 25 degrees Celsius. When concentration is not 1 molar, any other concentration, and temperature is not 298, then we can find out electrode potential of a half cell, and that is with the help of Nernst equation. So Nernst has given an equation which is E. This is E is electrode potential of an assembly, electrode assembly, and E0 is the standard electrode potential of that assembly minus RT upon NF, N small f capital, log E, concentration of RS. RS means reduced state. This is your reduced state, and upon concentration of OS. OS means oxidized state. So where this E is electrode potential of the assembly, whichever assembly you are using, zinc or copper or any other. E0 is standard electrode potential, which is reduction electrode potential, you know very well. R is the gas constant. This R is capital R is having value 38.314 joule per Kelvin per mole. The gas constant, you know, where T is temperature, absolute temperature, you know very well, Kelvin, temperature. N is the number of electrons gained or lost, and F is capital F is Faraday, that is equal to 96500 coulombs. Okay, and this is concentration of the substance obtained on reduction. Reduced state is concentration of reduced state means concentration of the substance obtained on reduction, and concentration of oxidized state is the concentration of substance undergoing reduction. So remember this Nernst equation, and now I'll teach you its application. So I will use that common cell galvanic cell that we have seen previously for different examples, cases, and that reaction assembly we have of zinc and copper. But this Nernst equation which we have, if I apply for this reaction, that is your reduced state of the substance. As you know, electrode potential is always found out as reduction potential. This is all I have mentioned in the previous class. So if a metal which is having valency N gains N electron, it is reduced to this state. So this substance is obtained on reduction and this substance is undergoing the reduction. So Nernst equation can be written for this equation, that is electrode potential, reduction potential of this electrode. Here no zero means what? It is not at standard condition, is equal to standard electrode potential, that is standard reduction potential of the same electrode assembly, minus RT upon NF log E reduced state concentration upon oxidized state concentration. If we solve this exponent, you have not to show all the step, you can write directly the value, and we write down the values of all this constant. R is a constant, F also is constant, and if we take temperature to 98, okay, then in that case we will have E0 reduction, standard reduction potential 8.314 into 298 upon N, F is 96500, that much coulomb. And if we solve this, we'll have multiplied with 2.303, and here it is continued here, log base 10 concentration of reduced state upon concentration of oxidized state. So this is the whole equation. Okay, so if this is solved, this whole thing is solved, we obtain E0, that is reduction potential standard. On solving all that value, we get 0.059 upon N log base 10 concentration of reduced state upon concentration of oxidized state. Our reduced state is this and our oxidized state is this. So that we have written, this is aqueous, this is aqueous, and this is aqueous. So this is your Nernst equation which is used for numerical. If T is not 298, then accordingly you will have to, you can use this formula if T is 298. Okay, if T is not 298, then you will have to put up the value of R and T and F individually. Okay, so this formula is the simplified form of Nernst equation. So the application of this I will teach you, that is with the help of Nernst equation you can even find out cell potential. E cell. You have seen last time, standard cell potential is equal to E0 cathode minus E0 anode. I hope you remember this formula, where this is reduction potential, standard reduction potential of cathode, and this is also standard reduction potential of anode. So both are reduction potential, standard reduction potential. So when we are going to use Nernst equation, then means your concentration is not 1 molar. So if I have a cell like this, which I showed to you, zinc solid over zinc ion aqueous, which is having concentration C1, where C1 is not 1 molar, separated by a salt bridge, copper ion aqueous having concentration C2 is containing copper solid as electrode, and electrons are flowing from anode to cathode. So this is our anode and this is our cathode. Okay, so this is right hand cell, this is left hand cell. Okay, so for this, when the concentration is not 1 molar, and if you want to know electrode potential of this half cell, you can make use of Nernst equation. So I'll write now for zinc assembly or zinc half cell, or for left hand half cell, what we have according to Nernst equation. Nernst equation. So I'll here rub this all, and because board is small, so I'll start right click after that. So Nernst equation, how it will be? Electrode potential of zinc ion over zinc means reduction potential, electrode potential, reduction electrode potential, which is not standard, is equal to E0 Zn over zinc, standard reduction potential of this, minus 0.059 upon, you can see electrons, if you write the equation for this, I have taught you to write equation. So 2 electrons are being lost and 2 electrons are gained. So value of N will be 2. Okay, and here we will have log base 10 concentration of zinc solid. This is reduced state and this is oxidized state, aqueous. Okay, so this is your equation 1. Then equation 2, that will be for this half cell. So you can write now for copper assembly, we will have reduction potential of copper is equal to standard reduction potential of copper minus 0.059 upon 2 log base 10 and copper solid upon copper ion aqueous. Now student, here I will put up the values of this zinc solid and zinc ion aqueous. Zinc solid, that is concentration of this. This is solid, so its concentration is taken to be unity. So the concentration, you can write that since Zn is solid, so concentration of zinc solid will be is equal to 1. So here I will take 1 and this concentration is given your C1. Okay, and here this will be unity and this concentration is, we have taken C2, so it will be C2. And this is your equation 2. Now we will use these two equations. Through this you can find out electrode potential of this half cell and here of this another half cell. And now you can find out cell potential. So cell potential you can find out, you know that E cell is equal to E right, or I write this way, E cathode minus E anode. When this is not standard, these will also not be standard. So cathode is on the right hand side, so you can write as E right. Anode is on the left hand side, so you can write it as E left. Okay. Now we will substitute their value. So what is at E right we have? We have copper, reduction potential of copper. So reduction potential of copper you can write like this, and reduction potential of zinc you can write like this. Now the values of these two you will put up from here over here. Okay, so that I am going to do for you. So here E cell is equal to E0 copper ion over copper minus 0.059 upon 2 log base 10 and 1 upon C1. This is one equation. This is C2, not C1, C2. For copper we have taken C2. So this is your, this half cell. Now minus this half cell E0 Zn. This I am substituting these values from equation 1 and 2 which I have done previously. If you have noted down, you can look back. Zinc minus 0.0592 log base 10 1 upon C1. This concentration sign won't be there because this is already the value I am putting. So this is C1. Then if you open the bracket, the sign will be changed. This is minus and this will become plus. Okay. Now if you remove this bracket, then you can take the things common. So this is equal to, if I take this and this, E0 copper ion over copper minus, if I write this together, zinc ion over zinc, this minus this. Then this is common. If I take minus 0.059 upon 2 common and the log base 10 also common, then I have got, this is your plus and this is your minus. So this will be going up. We will have C1, no bracket, C1 upon C2. C1 upon C2. This is your zinc ion concentration, this is copper ion concentration. So we have obtained this equation And you know this is our what? E0 cell. So you can say that E cell is equal to E0 cell minus 0.059 upon 2 log base 10 C1 upon C2. Okay. So in this case, this is your final equation. Equation 3 you can say for numerical. So remember that here temperature, this all I have mentioned to you, temperature is different. You will have to take that RT upon NF equation. So this is here, and this is the application of a galvanic cell which is of copper and zinc. Or you can take, this is for that galvanic cell when both the half cells have the metals which have the same valency. Valency of zinc is 2, valency of copper is 2. So this you can use for any galvanic cell when both anodic metal and cathodic metal have the same valency. Now the second application, when the valency of the metals in the two half cells or in two electrode assemblies are not same. So I give you an assembly that is cadmium. This is also common one. Cadmium solid over cadmium ion aqueous, which is having concentration C1, separated by a salt bridge containing silver ion aqueous and having concentration C2, having electrode of silver, and electrons are flowing from this half cell to that half cell. So this is anode, this is cathode. This is your right hand cell, this is left hand cell. You can notice the valency, cadmium valency is 2, silver valency is 1. So metals in different electrode assembly are not having the same valency. So we will apply now Nernst equation for this half cell. So what we will have? E cadmium ion over cadmium is equal to E0 cadmium ion over cadmium minus 0.059 upon how much, that I will tell you n value, log base 10, and since this is cadmium, so cadmium solid upon cadmium ion aqueous. Now to know this, here you can't take 2 because here 1 electron, so you will have to show. So you will write the reaction before this. Okay, I am writing here, or you can write it in the middle also, no problem. Cadmium will lose, cadmium solid will lose 2 electrons and will be turned into cadmium ion. This is your oxidation half cell reaction. Then silver ion aqueous is taking up 1 electron and is turning into silver solid. This is reduction half cell reaction. Now we will write overall reaction, that is cell reaction. This is half cell reaction, this is half cell reaction, oxidation half cell reaction, reduction half cell reaction, and here now overall, that is cell reaction. So number of electrons must be the same, lost and gained. So here that this equation we will multiply by 2. to make this true. So 2 electron cancel. Number of electron loss will be gained. So we have got cadmium solid. We have this reactant multiplied with 2. So it will be 2Ag ion aqueous. We will have cadmium ion aqueous, and we will have silver solid, but silver will be 2 Ag. So how much electron you will take? 2. Now you can write 2 since we have shown it. Okay. Now I will write for that silver. For silver, we will have E silver ion over silver, E0 silver ion over silver minus 0.059 upon 2, same, that is log base 10 concentration of silver solid upon concentration of silver ion aqueous. But silver ion is 2, so you have studied in class 11. This concentration will be raised to the power 2. I hope this is clear to you. So we have got these two equations, and now we will find out the cell potential. So E cell is equal to E right minus E left. What is at E right? We have E silver ion over silver, and E left we have a cadmium ion over cadmium, reduction potential for both. Now I'll substitute the value. So on substituting the value, here we will have E cell is equal to, for this one, E0 silver ion over silver minus 0.059 upon 2 log base 10. We have concentration of silver solid upon concentration of silver ion aqueous. This is taken to be unity, as I told, it is solid, and this concentration I have taken C2. So we have this equation. Then another equation we can write, this was not E cell, sorry. This will be E silver ion over silver, because first we have to write for this half cell, or directly we can do E cell, no need to do it again and again. So this is here. So this is one thing, this is E right and minus E left. So E left will be E0 cadmium ion over cadmium 0.059 upon 2 log base 10 1 upon C1. Concentration of cadmium we have taken C1. So if we solve this, we will have E0 silver ion over silver minus E0 cadmium ion over cadmium, and if this I remove, so this is minus, this will be plus. So if I take common, I will have minus 0.059 upon 2 log base 10 C1 upon C2. This is plus, this is minus. So C1 upon C2. So this is, you have a E0 cell. minus 0.059 upon 2 log base 10 C1 upon C2. This is E cell. So cell potential of a galvanic cell you could find out when conditions are not standard with the help of with the help of Nernst equation. In two conditions, when the metals of the two half cells do not have the same valency, and the previous case you saw when the metals have the same valency. So that's all for today.